all of you to the eighth session of the webinar series of Department of Chemistry. Today we have a scientist, Dr. Suresh C. Pillai from an institute outside India, that is the Department of Environmental Science, Institute of Technology, Sligo, Ireland. This session is session chair is our Professor Dr. G. Unnikrishnan. So let me introduce him first. Dr. Unnikrishnan is a professor in Department of Chemistry, NIT Calicut. He received his PhD from MG University, Kottayam, Kerala. His current research interests include design and development of novel macromolecular architectures, synthesis and characterization of pi-conjugated polymer systems, nanomaterials, transport phenomena, polymer membranes, novel catalysts for organic reactions and materials for physical medicine and rehabilitation. Dr. Unnikrishnan supervised 30 PhDs. 5 PhD scholars are currently working in the group. He has authored 264 technical articles, and he completed 12 research projects funded by MHRD, DST, STEC, CSIR, British Council, etc. 4 patents have been derived from his group. His group developed 2 inner liners for CTV orthosis and Knight Taylor's brace in association with the Calicut Medical College, Kerala. He is a recipient of Shankarlal Memorial National Seminar Award, IIT Kharagpur, and the Best Performer Award, NIT Calicut. He was a visiting researcher at the Department of Chemistry, University of Leeds, UK. He had combined research programs with Lunghai University, Taiwan. He has current collaborative programs with different universities and institutes. In the administration also, he served as a dean of student welfare in NIT Calicut. He is the founder secretary of Calicut chapter of Society for Polymer Science India, and currently he is the president of Society of
Hello. 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 Dr. Suresh, is it audible?
Yes. Yeah, yes, sir. I can hear you.
Okay. Sir, please.
Yeah. Very, very good afternoon, all. So thank you, Dr. Sujit, for the kind words. In fact, this this webinar series is voted by Dr. Sujit, headed by Dr. Sujit, Dr. Paramesh, and all our colleagues in the department. It is going on very well. We get good people like Dr. Suresh C. Pillai for this program. So it is being appreciated by many people. We find that this is a very useful program, and we are very happy to receive the consent from Dr. Suresh C. Pillai amongst his very tight schedule today. So Dr. Suresh C. Pillai, in fact, does not need any formal introduction in the Indian scientific community. He's one of the most popular scientists, Indian scientists working abroad. And he took his PhD from Dublin University. It was from Trinity College, Dublin, and later he was a postdoc at Caltech, California Institute of Technology, USA. He then returned to Dublin again as a research fellow, and in 2004 he joined Crest DIT as a senior scientist. That was in 2004. Then he joined the current organization in 2013, I think. So over the years, we have been maintaining very, very good contacts. In between, he completed, normally scientists, he completed a beautiful MBA program in 2009, again from Dublin City University. You might have seen his citations, high impact through Google Scholar. He has more than 5 million euro projects, more than 5 million euro projects. And he received recognition from across the globe. In 2019, he got Boyle-Higgins Award from Institute of Chemistry, Ireland. He got Industrial Technology Award in 2011, and for licensing functional coatings for Irish industries. He got Hot House Commercialization Award in 2009 from the Ministry of Science and Technology there, and a large number of awards are there to his credit. He is a member of ISO Standardization Committee. When you view his credentials, you would be glad to see a large number of publications with huge impact and large number of patents too. So his contributions, he's an extensive traveler, and he would love to speak to scientific members of the scientific community and students across the globe. So recognizing his interest, passion, and credentials, many major media covered his features, typically BBC World, BBC London, RTE1 TV, etc. Then the newspapers, The Guardian, Irish Times, etc. And most importantly, he is currently the editor of the Journal of Environmental Science and Pollution Research. He is in the editorial board of Chemical Engineering Journal and the Applied Catalysis D. And he's every time he comes to India, he takes care to address students and faculty to intellectually stimulate them, to generate a scientific thought in them, to generate passion for doing good chemistry. And last year also, I think we have had 2 programs together in Kerala, 2 different locations where his lecture was appreciated and received by many people. We get very good feedback on his performance and the dedication he shows for doing science. In addition to that, he's an extensive writer. He writes in many columns. In Malayalam Manorama, that's a Kerala daily, he regularly writes in a column called Science Cafe. That is a so popular program that last time when he visited, I will tell you an incident, 2 minutes time. When he was traveling in an auto in Calicut city, he got into auto, they traveled together. At the destination, auto was stopped. He was about to pay the driver. The driver said that, no, sir, I will not receive money. You are Dr. Suresh Pillai. I know that you are handling the Science Cafe. So it was true. Suresh was. I do not know how to express those moments. So he's a popular scientist living down to earth. So Dr. Suresh, we are extremely happy to receive you this afternoon. We are thankful to you. We would love to continue our association for a long time. With these words, I would love to welcome Dr. Suresh Pillai, all the participants and the department. Over to Dr. Suresh.
Thank you very much, Dr. Unnikrishnan and Dr. Sujit for the invitation and for the kind words. I'm thinking around 25-30 years back to MG University hostel, where I used to live very close. I was very fortunate to live very close to Dr. Unnikrishnan's room in MG University hostel. Jamat and Dr. Jammati was all these pioneers in science, you know, and that was inspired me. The talk we had in the night, 12 o'clock in the midnight, Jamat used to come very late night, and then he used to talk for 5-10 minutes to me, and same as Dr. Unnikrishnan, Sri Krishna Kumar, all these, like, and Vijay Lali, he is a counselor now. So the influence that imposed on me tremendous. So I was mentored, even though I was an MSc student that time. They were all kind of PhD scholars. So the inspiration I got from Unnikrishnan and his colleagues was huge. I can never forget about that. We had gone through a lot of ups and downs during that time also. We had a lot of like financial difficulties, and life was not easy at that time. So I remember the courage and the motivation Dr. Unnikrishnan gave that to me during more time. Is it visible now?
It's slowly coming.
Okay.
Yes.
Okay. Now it's come. Okay.
Can you see it now?
Yes,
Yeah,
fine, sir.
Perfect.
Okay. So 1 nanometer means it's 1 billionth of a meter. So which is equal to 1 billionth means 1 over 1 followed by 9 zeros of a meter, or equivalent to the length of 10 hydrogen atoms. So we are talking about very small particles. So let us look into it. Let us take a hair, touch your hair and then feel it. I don't have much hair left. So if you want to touch one of your hair and then feel it, how small it could be. Okay. So the dimension of a human hair is equal to 20 to 50 micrometers. Okay, that's very small. Or if you put that in nanometers, it is 20,000 to 50,000 nanometers. For argument's sake, let us take it as 50 micrometers or 50,000 nanometers. So if you want to get 1 nanometer, so you have to slice that or slice your hair into 50,000 times vertically. So you take your hair and slice that to 50,000 times vertically, and then one part of that would be 1 nanometer. So 1 nanometer is one part of 50,000 slices of your hair. So this is very tiny particle. So how small is the biological world? How small is small? Richard Feynman, in his famous talk he delivered in Caltech, in California Institute of Technology in 1959, he said that there is plenty of room at the bottom. And you can decrease the size of things in a small way. So if you look into the biological world, the smallest visible length to the human eye is 10 micrometers across. So we will not be able to see anything below 10 micrometers. So obviously we are not going to see nanoparticles using our human eye. If you use a light microscope, you can see up to maybe 1 micrometers. And if you want to see anything below that, you need an electron microscope. For example, lipids, proteins, viruses are around 100 nanometers. Bacteria is in the region of 1 micrometers to 10 micrometers. So you should be able to see the bacteria using a normal microscope. So nanomaterials and nanotechnology has a huge amount of applications. For example, in energy storage, for communications, electronics, biomedical and drug delivery, agriculture, food, cosmetics, paints, textiles, optical engineering, you name it. Nanotechnology find applications in a wide range of areas. So why nanomaterials are important? I don't know if you remember your school mathematics, the surface area of a cube. Surface area of a cube is 6a squared. Yeah. So if you take 1 centimeter cube, the total surface area would be 6 centimeters square. So I'm going to slice that 6 centimeters cube into tiny 1 millimeter cubes. So then the total surface area would be 60 centimeter square. So in a similar fashion, if we slice that 1 centimeter cube into a number of 1 nanometer cubes. The total surface area would be 60 million centimeter square. So that all 1 million nanometer cubes. So that is the beauty of nanomaterials. They will have huge surface area, and that has huge implications in electronics, where most of the electronic devices work based on the grains and grain boundary, the control at the charge at the grains and grain boundaries. So if you increase the surface area, you can make devices with better properties, with improved properties. In electronics or in drug delivery, so every aspects of nanotechnology has applications based on the high surface area of these materials. So how do you prepare nanomaterials? I understand that most of you are chemists. So in a conventional way, the nanomaterials are prepared from slicing down the bulk of the bulk materials. So you take the bulk material, you powder it or you mill it, you make nanoparticles. But we are chemists. We play with molecules. So using molecules, or we call it as precursors, you can make clusters using chemical reactions. And then from these clusters, you can develop nanoparticles using a wide range of technology, and either using a conventional oven or a conventional furnace, or you can use a microwave oven, or you can use a sonometer, or you can use the conventional precipitation techniques to develop this nanoparticle. So that is the advantage of being a chemist. So being a chemist, you can contribute a lot in the area of nanotechnology. So that is one of the reasons. If you look into any high impact papers, any recent innovations in nanotechnology, a significant part of it is done through chemistry. So chemists can play a huge role in developing novel materials, novel nanomaterials. So don't underestimate the power of chemistry. So these are some of the, and we can develop these nanomaterials. We can tune these nanomaterials into different parts. So this is a part of the work I did in Trinity College. My colleague did a lot of work as well. Sibu, I talked to Suni earlier. Suni and I worked with the same supervisor there, Professor John Kelly. So we did a lot of work on developing different shapes and morphology of nanoparticles, nanowires. Like this is the work my colleague Sibu did. Nano needles, nanospheres, like a sphere-like structure. Like you can develop a range of different size and shape of materials by tuning the properties or tuning the precursors or tuning the reaction conditions. There's a lot of areas to play. It's fun. It's fun to work on materials. It's fun to work on nanomaterials. So we discussed that nanomaterials can be used for a number of applications. I'm more interested in environmental applications of nanomaterials. So what are those? So when we talk about nanotechnology, we often think about this nanotechnology is mostly used for making electronic devices. So making the computers smarter, the smartphones, or electronic devices. We often forget about the use of nanomaterials for environmental applications. So that is what we are going to discuss in the next few minutes. So I'm working in the area called photocatalysis. So this is where we use the nanoparticles for environmental applications. So what is photocatalysis? You may have heard about photosynthesis. Many of you are not familiar on photocatalysis, but you have heard about photosynthesis. So we studied in the school that when light hits leaves. Leaves have chlorophyll in them, and in presence of carbon dioxide and water, carbohydrates, oxygen, and water are produced. So that is a very simple and straightforward photoreaction. So we can compare the photocatalysis in a similar manner. So in photocatalysis, we use semiconductor materials such as titanium dioxide. And these materials are definite, valence band, and conduction band. So when you heat or when you irradiate these materials with certain wavelength, we can discuss that wavelength in a minute. So let us say that when the semiconductor materials are irradiated with UV light, an electron moves from its valence band to the conduction band. So look at the electron's place now. The electron is at the conduction band. So which means that a hole is created in the valence band. When you move an electron from the lower energy level, which is the valence band, to the higher energy level, which is the conduction band. So you create two species. One is an electron and one is a hole. Both of these has lot of potential for a number of reactions. So we are finding an opportunity there to use these two reactive species. For example, the electron, which is available in the conduction band, to react with oxygen to form superoxide anions. And these superoxide anions can further undergo reactions to form singlet oxygen. And in the valence band, we have the hole, and the hole can react with water molecules in the atmosphere. So we have a lot of moisture in the atmosphere, and it reacts with water to form hydroxyl radicals. So you can develop a lot of number of oxidation and reduction reactions. For example, if a pollutant is exposed to this condition, that pollutant can be degraded, because these are called reactive oxidation species. These are highly reactive. Superoxide anions, hydroxyl radicals, singlet oxygen, these all can react with, these are very powerful. They can break the bonds. They can convert complex organic molecules into smaller molecules. And they can continue the reaction until it forms smaller molecules such as carbon dioxide, water, ammonia, like that. Okay, we discussed that when these materials are exposed to radiation, for example, UV light, the electron moves from its valence band to the conduction band. So we'll talk it in detail in a few minutes, how this happens, what are band gaps and all. Before that, just remember this. If you reduce the band gap, if you add additional energy levels between the valence band and the conduction band, we can use visible light, because ultraviolet light is not feasible at all conditions. For example, if you want to depollute a region, or for example, if you want to decontaminate a room using these semiconductor materials, it's not practical to put UV light there. But if you develop a material which works in the visible light region, that will have more advantages. So that is why we have to add additional energy levels between the valence band and the conduction band. So that is how we can use the visible light. So we have been working in the past few years to develop visible light active photocatalysts. So photocatalysis is the reaction of an acceleration of electrons in presence of a catalyst. Or the reaction is initiated by the movement of the electron from its valence band to the conduction band, and then its continued reaction with oxygen in the atmosphere, and also the reaction of hole with water. So you are creating a range of reactive oxidation species. So before moving to further, we have to look into the time. How often or how quickly it happens. And then only we can see that how we can control these reactions. Because what usually happens is that when the electron moves to the valence band, which is a lower energy level, to the conduction band, to a higher energy level, using a radiation. So normally what would happen? The electron can come down. Naturally, because you are going from a lower energy level to the higher energy level. So obviously, the electron will come back to the normal level. But we don't want that to happen, do we? What we need, we want to use these electrons and holes for reactions. So our aim is to keep that electron away from the valence band. So let us look into the time. Then only we can find other protocols or find proper strategies to control the electron hole recombination. We don't want the electron hole recombination happening. We want to keep them away as much as possible. So the generation happens in the range of femtoseconds. And the recombination happens in nanoseconds. So there's a huge time gap. Even though it is nano and femto, in the reaction scale, it is hugely different. But if you use a trap, the trapping can happen in the bulk, it is 500 picoseconds, or in some cases 260 femtoseconds. Forget about the numbers. So the trapping could be much faster than recombination. So if you find a good trapping, for example, copper metal is used as a trapping agent. Silver can be used as a trapping agent. Silver ions. So these silver ions can trap the electron. So it can hold the electron for a while so that the hole can do the reaction. It's a bit complicated. Two boys at home, Sri Hari and Sri Shekhar. So when they come back from school, they have to do a lot of homework. So Sri Shekhar goes upstairs and Sri Hari stays downstairs to do his homework. Sri Shekhar is a small child, like he's only 10. He has only a small amount of homework to do. So he can finish everything in half an hour. But Sri Hari he's in the secondary school. He has a lot of homework to do. So what happens is that immediately after finishing the homework, he will come down. I don't want to see that because there will be a lot of distraction if he comes down. So what I will do, I will play with him for another half an hour. So my role is a kind of silver ion. And Sri Shekhar is the electron. So I'm trying to keep him there as long as possible so that Sri Shekhar can do Sri Hari can do his homework. Same way. So the electron goes to the higher level. We don't want the electron to come down. So we want to keep the electron there as much as time as possible. So we can use trapping agents to keep it there. So this is one way of increasing the productivity. So if you want to increase the productivity of Srihari, I want to keep Srishagar in his homework room or in his room for a while. This is exactly happening in photocatalysis. So if you want to keep the electron in a hole active for reactions, we want to trap the electron. It can happen the other way as well. So we can trap the hole so that the electron can engage in other reactions. Okay, so trapping is one way of controlling the photocatalysis. Okay, so before going into further, I can give you examples of photocatalytic materials used in the market. So, you had a hot shower in the morning. You went to the bathroom and you used the hot water. And if you have a mirror in the bathroom, what you would see? A lot of mist. So you cannot see the mirror properly. Say, look at this figure. Can you see the picture here? So we are seeing two glasses here. So in the first glass, that's a normal glass. You can see a lot of water droplets there. In the second glass, there are no droplets. So this first one is a normal glass and the second one is a photocatalytic glass. So what is happening there is the normal glass is hydrophobic, which means it doesn't like water. Phobic. So when you spray water over it, it will form as droplets on the surface. But if you use a photocatalytic material, there wouldn't be any droplets. The water droplet will form a thin film over the glass. So you wouldn't even notice that. So that is what's happening with the photocatalytic glass. So if you use a photocatalytic glass in your bathroom, so after the hot shower, you can easily see in the glass. So there wouldn't be any mist. Whatever mist formed on the surface will form as a thin film. And it has a huge amount of applications. On a rainy day, you start your car. You look at the rear view mirror. What would you see? A lot of droplets on the mirror. Now, in many of the modern cars, they use the photocatalytic glass so that there wouldn't be any droplets formed on the glass. It will be a thin film. So what's happening there? We are chemists. So we need to understand what's going on there. So for the photocatalysis, we use a material called titanium dioxide or TiO2. So titanium is in the +4 state there. When you irradiate titanium dioxide, what happens? We discussed that electron moves from its valence band to the conduction band. Some of the electrons can be used for reactions, which means that the Ti4+ state of titanium will change to Ti3+. So we know that titanium dioxide is TiO6 2- octahedra. So just think that TiO2. So if the Ti4+ changes to Ti3+, what will happen? Some of the oxygen has to leave the surface in order to keep the stoichiometry. So that will create oxygen vacancies on the surface. So once you have oxygen vacancies, the water has a lone pair of electrons. The water can easily fit on these oxygen vacancies. So we are moving from hydrophobic to hydrophilic. So because of the oxygen vacancies, the water molecules can easily fit on those surfaces. So that is how we can convert a hydrophobic surface to a hydrophilic surface. The beautiful chemistry there. And these materials can use for a number of other applications as well. For example, for killing the bacteria. We discussed that when the electron moves from its valence band to the conduction band, a range of reactive oxidation species are formed. And these reactive oxidation species can attack the cell membrane because these are complex organic molecules, biomolecules. It can react with these biomolecules. And they can eventually kill the bacteria. It can rupture the membrane of the bacterial cell wall. It can go into the cellular material of the bacteria. And the metabolic properties of the bacteria will be disturbed. It will damage the DNA and RNA. And finally, theoretically, the bulk biomolecule of the bacteria will be converted to simple molecules such as carbon dioxide or water or other simpler molecules. So with photocatalysis, we can kill the bacteria. We can disinfect the surface. We also heard that a number of other materials are used as antimicrobials. For example, metal ions, silver. Copper is traditionally used as an antimicrobial material. There's a huge difference between the metal ion antimicrobials and the photocatalytic disinfection. In metal ion antimicrobials, this is just for your information, how does it work? For example, if you are using silver ions, these silver ions can react with enzymes inside the bacteria. So this silver obviously is positive, silver ion, Ag+. So this Ag+ can react with enzymes. And many of the enzymes contains thiol groups, SH-. So these silver ions can react with these minus groups in the enzymes. And that deactivate the function of the enzyme. And that will disturb the biological properties, its biological functions, its metabolic activities, and eventually the bacteria will be killed. But the problem is that the debris after the killing of the bacteria will still be remain there. And eventually a lot of debris can form on the surface. But the beauty about photocatalysis is that we can remove the debris as well, or the toxins produced after the death of the bacteria can also be removed by photocatalysis, because photocatalysis is a continuous process. It's a molecular process. It attacks the biomolecule. So it keeps on working until the simpler molecules are formed. So the photocatalysis is a very effective mechanism for disinfecting the surface. Sorry, Dr. Sujit, how much time I have?
No, sir, you can continue. 10 minutes you can continue, bro. 10 more minutes.
Okay, 10 more minutes. So I'll finish in 10 more minutes. Okay. Okay, thank you. Okay, so in 10 minutes, I'm going to show you a case study, how these simple techniques can be used for commercial applications. So far we have talked about chemistry. I have been using my hat as a chemist. So I'm now taking that hat as a chemist from my head, and I'm putting my business cap there. So I'm going to show you how these simple chemistries can be used for commercial applications. So, as a chemist, I was only looking at the chemistry side of that. Now I'm looking, why couldn't I commercialize it? What are the limitations? So the limitations of photocatalysis are we discussed earlier, because it has limited activity in the visible region because of the band gap. The band gap is 3.2 electron volt, which means it can only use ultraviolet light, UV light. So we cannot use it for practical applications. You cannot put it in an operation theater, or you can put it in a classroom. It's not practical to put UV light. But if you develop a titanium which work under visible light, that will have huge advantages. And also a commercial aspect. So if you are going to develop ceramic tiles, you have to make this material stable at high temperature. For example, if you are developing bathroom tiles, for example, because we know that a number of infections are contaminated through the surface. One classical example is ceramic tiles, bathroom tiles. So if you want to coat these materials on ceramic tiles, you have to make these materials stable at high temperature. Why? Because these tiles are sintered at very high temperature. Because during the manufacturing process, these are sintered at very high temperature, up to 1000 degrees Celsius. The problem here is, so I'm going to skip a few slides. The problem here is the anodized form of titanium dioxide, which is a normal state, convert to rutile, which is a non-photocatalytic phase at high temperature. So you cannot use the normal photocatalytic material, which changes to a non-photocatalytic phase at 6. So that is one problem. The second problem is visible light activity. So we discussed that the band gap of titanium is 3.2 electron volt. So look at the classical equation, E is equal to hc by lambda. Lambda is the wavelength. So if you put all the figures there and put the band gap of titanium, you can see that it's the 387.5 nanometer, which means if you want to irradiate the titanium dioxide, you need to use UV light. So look at the denominator here, 3.2. So if you reduce that, this can be increased. 387 can be increased to 400 and 420 or 430 or 450, depending on the band gap. So that is what we are seeing here. So if you reduce the band gap, you can use visible light. Okay, so we are going from chemistry to a little bit of physics. In other words, if the band gap is too high, it's very difficult for the electron to travel. It struggles to move. But if you minimize the band gap, it's easy for the electrons to travel. So this is where we use chemistry. So we have to identify a number of dopants which can form an additional level in between the valence band and the conduction band. So that is what we have been doing in the past 15 years to identify different types of dopants to fill the gap, or making additional steps like this, so that it is easy for the electrons to move from its lower level to the higher level. So I'm going to skip a few slides. Okay, so in order to reduce the band gap, we need to look into our chemistry notebooks or inorganic chemistry books, Cotton and Wilkinson or something similar books. We need to see the molecular orbital diagram. What's going on? How the hybridization is happening? What is made up of the valence band and what is made up of the conduction band? What are the dopants we can use? So you need to do a lot of modeling work. simulation work. So you need to work with your colleagues who are doing DFT studies. So they can calculate the energy levels. They can come up with solutions to identify which type of dopants we can use to fill the gap, the valence band and the conduction band. For quickly, I can say that the valence band of the titanium is by O2P levels, and the conduction band of Ti 3D levels. So this information is very, very important to calculate the energy levels of the materials you have to fill between the valence band and the conduction band, so that the energy level can be further reduced. Okay, so I'll finish in 5 minutes. So these are some of the materials we have used. Anodized to rutile heterostructures, anodized to brocates heterostructures, oxygen-rich titanium dioxide. So we have developed a range of materials which can form additional energy levels in between the valence band and the conduction band. For look at this example, we have used nitrogen and sulfur doping. So this can form as an additional level in between the valence band and the conduction band. So N2P, for example, will form an additional energy level above 0.14 electron volt above the valence band. So you are creating a number of additional steps. So it's easy for the electrons to jump from one step to another step to the conduction band. So you are making the job of the electron easier. So these electrons can be activated, or this semiconductor can be activated using visible light. So you don't need ultraviolet light for the activate, and that has a huge commercial potential. So we are changing the UV light to the visible light. So now we can use, after adding all these energy levels, we can use visible light. So we have developed a range of materials, doped materials, which can be added in between the valence band and the conduction band. So this is a paper we published in Physical Chemistry Letters back in 2011, and then there was a review paper on that. So I can share those papers with you if you are more interested. So you can email me, I can send you the review papers to you and have a read. So I'll finish in the next couple of minutes. So this is, we have developed all these technologies, we know how it works, and then a company came to us developing ceramic tiles for bathrooms. So they found huge business opportunities there to use for making ceramic tiles for bathrooms, toilets, in like big shopping malls or in airports and all. So the company came to us, and they wanted to develop these ceramic coatings on the surface. But still we had the other problem, high temperature stability. Even though we developed a titanium dioxide which can work under visible light, there is one more challenge remain. That was high temperature stability. Why? Because we discussed that the anodized form, which is the photocatalytic form, changes to a non-photocatalytic form, which is rutile, at a temperature of 600. So the processing temperature of tiles is 1000 degrees Celsius. So the next challenge was to develop a high temperature stable titanium dioxide. I'm going to skip this. So this is what happening, a photocatalytic phase, which is anodized. When you heat it at 600 to 700 degrees Celsius, a non-photocatalytic phase, which is rutile, is formed. So we have to find techniques and technologies to identify, or we have to come up with protocols to develop two things. One is high temperature stability and visible light activity. So we did a lot of work. I had a lot of students working with me. Pradeepan was one of them. Pradeepan is not too far from you. He's in Calicut University. Pradeepan was my first PhD student. Pradeepan did a lot of work, then Vinod did a lot of work, then Rachel, Nick. We had around 50 PhD students and postdocs working in this program. This is the combined work of around 25 to 50 researchers at different stages of their PhD program. We have developed a range of materials, the range of different dopants to as well as visible light activity. Then we have tested these materials. Then we found that what you see here is a lot of bacteria grown on the surface. That is a normal tile. So when you use this photocatalytic tile, we found that no bacteria formed on the surface. This is tested using MRSA, one of the dangerous bacteria. And also we tested it with an external agency. We found that 99.99% of the bacteria were killed. And then we have transferred this technology to a company, and then company started developing it. And this technology was developed, is awarded as the best, one of the 50 innovative technologies from Europe in 2011. So we have been awarded a number of patents. A number of patents are pending. This was attracted a lot of newspapers, and it was telecasted live in a number of TV stations. And then the technology is being commercialized by a company. So they have further developed it. So they are using it for various applications, including touchscreens and all. Custos is the company which is currently developing this material. They are employing a number of people there to work on these technologies. So that is all from my presentation. I would like to thank all my PhD students and postdocs who has really contributed to the work. And I also thank my collaborators. I have a lot of collaborators in Kerala as well. So I work very closely with CUSAT, Cochin University, MG University, and also I have collaboration in IT. So if you have any ideas, if you have any questions, I'll be happy to answer your questions. And this project was funded by Enterprise Ireland, Science Foundation Ireland, European Commission, and a part of this work is funded by National Science Foundation in the US as well. So thank you for listening, and I'll be happy to answer a few of your questions. Thank you.
Thank you, Dr. Suresh, for your excellent lecture. Very, very informative, very, very inspiring. Dr. Sujit advises the participants to look into the chat box for questions. I think 1 or 2 students have now posted questions. Could you please look into the chat box and write us?
Yeah, it's Manivarna